3 times 1 is minus 2. 0 times 1 plus 1 times 1 is 1. So A prime has coordinates minus 2, 1. Point B, 1 minus 3, 0, 1 times 3, 1 will give us 1 times 3 plus minus 3 times 1 is 0. 0 times 3 plus 1 times 1 is 1, and therefore B has coordinates 0, 1. Do the same with C. 1 times 2 plus minus 3 times 4 is minus 10. 0 times 2 plus 1 times 4 is 4. Therefore C has coordinates minus 10, 4. In fact, to save time, the vertices of the triangle can be put in 1, 2 by 3 matrix. And so we'd have the shear matrix 1 minus 3, 0, 1 times 1, 3, 2, 1, 1, 4. And then you proceed and multiply. We start with the x coordinates. 1 times 1 plus minus 3 times 1 is minus 2. 1 times 3 plus minus 3 times 1 is 0. 1 times 2 plus minus 3 times 4 is minus 10. Then the y coordinates. 0 times 1 plus 1 times 1 is 1. 0 times 3 plus 1 times 1 is 1. And then 0 times 2 plus 1 times 4 is 4. And so we have the matching coordinates. Notice that the y coordinates did not change because the displacement was parallel to the x-axis and there was no vertical displacement. Attempt the same transformation, but now with y-axis invariant. Notice that the shear matrices only work when the invariant lines is either the x-axis or the y-axis and not any other line. Any other line, the solution will have to be construction. In the same way, we can easily obtain a stretch matrix for x and y axis being invariant. Consider a stretch factor of 3 with x-axis invariant. What will be the stretch matrix? We go to the unit square and consider points I and j under the same stretch. In stretches, points move perpendicular to the invariant line and distances are taken from the same invariant line. Because x-axis is invariant, point I is invariant, and so it remains I prime 1, 0. What of point j? J prime will be image distance is equal to m times object distance. That is 3 times 1 giving us 3. So it will be 3 units from the invariant line. Its coordinates will be j prime 0, 3. As vectors, I prime is equal to 1, 0 and j prime is equal to 0, 3. As a matrix, that will be 1, 0, 0, 3. In general, the stretch matrix with x-axis invariant is given as 1, 0, 0, m, where m is the scale factor. If you repeat the same for y-axis invariant, the matrix will be m0, 0, 1. For example, triangle PQR with coordinates P1, 2, Q, 3, 5 and R3, 0 undergoes a stretch by factor -2 with y-axis invariant. Calculate the coordinates of its image. So the stretch matrix for y-axis invariant, in this case factor -2, will be -2, 0, 0, 1. We multiply by the coordinates of the triangle PQR and we'll find that P prime will be -2, 2, Q prime -6, 5 and R prime -6, 0. Next, Rotation matrices. Again, unless required to, you can avoid doing construction of figures when the center of rotation is at the origin 0, 0. We use matrices. To find the matrix, you get the same unit square and consider points I and J. Rotate the points through the required angle and get the new coordinates. Using them, form a matrix and you shall get the rotation matrix. For example, point P with coordinates 5, 7 is rotated through negative 90 degrees. Write the coordinates of its image. This is the unit square. We need to find the rotation matrix for negative 90 degrees. We rotate I and J, and this you can do with your eyes. Negative 90 degrees means clockwise rotation. If I is rotated negative 90, it will be here, I prime, 0, negative 1. If J is rotated negative 90, it will be here, J prime, 1, 0. As vectors, I prime is equal to 0, negative 1, and J prime is equal to 1, 0. As a matrix, that is 0, 1, negative 1, 0. This is the rotation matrix for negative 90 degrees about the origin. So we multiply the coordinates of point P with this one to get P prime. 0, 1, negative 1, 0 times 5, 7. 0 times 5 plus 1 times 7 is 7. Minus 1 times 5 plus 0 times 7 is minus 5. And so P prime has coordinates 7, negative 5. Attempt the same with a rotation of positive 90 and 180 degrees. Once again, notice that the matrices of rotation only work when the center of rotation is the origin, 0, 0. Reflection can also be done using matrices. We use the same unit square and reflect the points I and J. For example, consider point M with coordinates minus 9, 6 to be reflected on the line Y is equal to minus X. We find M prime. First, we find the reflection matrix for Y is equal to minus X. We get our unit square. The line Y is equal to minus X is this one. Now reflect I and J on that line. I prime will be 0, minus 1, and J prime will be minus 1, 0. As vectors, I prime is equal to 0, minus 1, and J prime is equal to minus 1, 0. As a matrix, that will be 0, minus 1, minus 1, 0. This is the reflection matrix for Y is equal to minus X. We multiply M with that. 0 times minus 9 plus minus 1 times 6 is equal to minus 6. Minus 1 times minus 9 plus 0 times 6 is 9. So M prime has coordinates minus 6, 9. And so you see, by using the unit square and transforming points I and J, we can create the matrices of transformation for special cases and calculate the coordinates of the images. Finally, the enlargement matrix. Now, the 2 by 2 enlargement matrix has the general form K0, 0K, where K is the scale factor with center of enlargement 0, 0. Any other center of enlargement cannot work with matrices. Recalling similarities and enlargements, K is the linear scale factor, and therefore K squared will be the area scale factor. For example, triangle ABC with coordinates A 3, 5, B 1, 1, and C 3, 1, and area 4 square units undergoes an enlargement with scale factor 4 with center of enlargement at 0, 0. Calculate the coordinates and the area of the image. So the enlargement matrix will be 4, 0, 0, 4. And then we write the coordinates of the 3 vertices as 1, 2 by 3 matrix. We then multiply by the enlargement matrix. If we do that, A prime will have coordinates 12, 20, B prime 4, 4, and C prime 12, 4. Area scale factor will be equal to 4 squared, giving us 16. And so the area of the image will be 16 times 4, giving us 64 square units. Next, successive transformations. Now, an object can undergo several transformations one after the other. This is done such that the image of the preceding transformation becomes the object of the next transformation. When an object A undergoes a transformation N, followed by another transformation M, this is written as MNA. The first transformation is the one next to the object. In this case, it's N. So the object first undergoes transformation N, and then the results undergoes transformation M. That order is very important. In fact, we can have a single matrix for both M and N by first multiplying them together. The resulting matrix R is then multiplied with the object. So given MNA, if Mn is equal to R, then Mna is equal to Ra. For example, a point P with coordinates 4, 5 undergoes a reflection on the line y is equal to x, followed by a rotation of negative 90 degrees about the origin. Find the coordinates of the final image. First is reflection followed by rotation. So we can represent that as TFP, where T is rotation and F is reflection. First, we work out TF. The reflection matrix on y is equal to x is 0, 1, 1, 0. The rotation matrix for negative 90 degrees about the origin is 0, 1, negative 1, 0. So T times F will be equal to 1, 0, 0, negative 1. Then we multiply this product with P. So 1, 0, 0 minus 1 times 4, 5 will give us 4 minus 5. And so the final point will have the coordinates P for negative 5. Next, inverse of a transformation. The inverse of a transformation reverses the transformation. This means that the final image is mapped back onto the original object. For example, if a figure is rotated positive 90 degrees, then the inverse is a rotation of negative 90 degrees about the same center of rotation. A matrix that maps an image back onto its object is called the inverse of the matrix of transformation. If M is a matrix representing a transformation, then its inverse is given as M negative 1. Therefore, given a transformation MA is equal to A prime, then M negative 1 times A prime is equal to A. Knowing the matrix of a given transformation, it is possible to know its inverse. For example, 1, 3, 0, 1 is a shear matrix of scale factor 3 and x-axis invariant. 3 represents the shear factor. The inverse of this matrix will be 1, negative 3, 0, 1. We change the sign of the element in the matrix representing the shear factor. 1, 0, negative 2, 1 is a shear matrix with scale factor negative 2, y-axis invariant. The inverse of this matrix will therefore be 1, 0, 2, 1. How about stretch matrices? A stretch matrix with scale factor m, y-axis invariant is given by m0, 0, 1, and with x-axis invariant is given by 1, 0, 0, m. M stretches the figure in a certain direction and thus changing its size. To reverse the image back to the object, we have to reverse the two things, size and direction. To change the direction, we reverse the sign. To change the size, we replace m with 1 over m. And so we have the inverse of m001 is equal to negative 1 over m0, 0, 1. And the inverse of 1, 0, 0, m is equal to 1, 0, 0, negative 1 over m. So 3, 0, 0, 1 is a stretch matrix of scale factor 3 with y-axis invariant. Its inverse will be minus 1 over 3, 0, 0, 1. How about enlargement? The enlargement matrix about the origin is given by K0, 0K. Enlargement changes the size. The image is K times the object. It means the object is 1 over K, the size of the image. And so the inverse of K0, 0K will be 1 over K0, 0, 1 over K. We do not change the sign. It means that the inverse of negative 2, 0, 0, negative 2 will be equal to negative a half 0, 0, negative a half. What about reflection? To map the image back onto the object, you simply reflect the image onto the same mirror line. So the inverse of a reflection matrix is the same matrix. Determinant of a matrix and area. Now, under some transformations, the size and shape of objects do not change, while in other transformations, they do. When a matrix represents a transformation, the ratio of the area of the image to the area of the object is equal to the determinant of the matrix of transformation. Therefore, image area over the object area is equal to the determinant. For example, a triangle with vertices A, 0, 0, B, 4, 0, and C, 4, 3 is transformed under the matrix 1, negative 2, negative 1, 4. Find the coordinates of the image and the areas of the two figures. If we multiply the coordinates by the matrix of transformation, we shall get A prime is 0, 0, B prime will be 4, negative 4, and C prime will be negative 2, 8. Area of the object. The object is a right-angled triangle with AB and BC being perpendicular. AC is the hypotenuse. If you look at the coordinates, AB is equal to 4 units along the x-axis, BC is 3 units parallel to the y-axis. Therefore, area is equal to a half times 4 times 3, giving us 6 square units. Area of the image over the area of the object is equal to the determinant. We already have the area of the object, 6 square units. The determinant, we multiply 1 times 4 minus 1 times 2. That is 4 minus 2, giving us 2. And so the image area over the object area is equal to 2. Image area over 6 should be equal to 2. Cross multiplication, and the image area is 12 square units. So in summary, to transform a point xy by a matrix A, B, C, D, we multiply the two matrices A, B, C, D times X, Y. To find a transformation matrix, we use the unit square. We take I and J and transform them, and we will get the matrix. There are 6 types of transformations: shear, stretch, translations, rotations, reflections, and enlargements. Shears move points parallel to the invariant line. The general shear matrix with x-axis invariant is 1s, 0, 1, and with y-axis invariant it's 1, 0, s1, where s is the shear factor. Stretches move points perpendicular to the invariant line. The general stretch matrix with x-axis invariant is 1, 0, 0, m, and with y-axis invariant it's m0, 0, 1, where m is the scale factor. Translations are represented by a vector, or you can see it as a 2 by 1 matrix. To translate a point xy with vector AB, you simply add the 2, xy plus AB. The general enlargement matrix is K0, 0K, where K is the scale factor or the linear scale factor and K squared the area scale factor. Notice that K squared is the determinant of the matrix. Rotation about the origin and reflection matrices are determined using the unit square. The inverse of a matrix will map the image back onto the object. The determinant of a transformation matrix gives the scale factor for area. A singular matrix, that is one with a determinant of 0, will map all points to a straight line.
I love that math generally has initially clear and precise answers, that you know when you know it and you know when you don't know it. As you get farther on in it, the answers are not so clearly in the back of the book, but initially math has answers, clear answers. Sometimes they're hard to find, but that clarity. The second thing I love about math is it's a puzzle-solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle-solving kind of thing that I really, really like.